So today we will discuss law of large number. We earlier proved law of large number, but we assumed that the second moment exists. We will give us no. That's a strong law of large number. We will prove weak law of large number only now. So again, strong we will not prove without that. So for that we assume second moment exists. So without that we will prove now. Only expectation exists. Assuming that. I mean the proof is easy. We want to see some easy proofs, right? So then we will prove the central limit theorem. So these are the two things we want to do next. Before that, I will just give a counter example. I mean, we know almost for convergence. I mean, I want to give a counter example, not counter example. I want to give a what do you want to say? Convergence in probability implies there is a subsequence which converges in almost surely. Okay, just I will give that, and then we will move to that. So this is proposition, this is a very useful proposition which is used in many places. So better. There are more types of convergence. Convergence in mean, convergence. I mean, if xn converges to x, if expectation of xn minus x, this goes to 0, or if it converges in nth moment or nth mean, if xn minus x power n goes to 0. So there are this kind of definition also, and there are more facts and theorems we can prove, but we don't have too much time. So I will just prove this. I mean, here also, if it converge, almost sure convergence will not imply this, because of dominant, you need some conditions. Almost sure, then there should be some dominated conditions, dominance conditions here, then only you can prove this. So on the other hand, the converse is also not true, but if this converges, then there exists again a subsequence which converges almost surely. If it converges in mean, then there is a subsequence. But that will anyway follow because this will imply the convergence in probability. Okay. So from that, this is the main fact. So xn is a sequence of random variables such that xn converges to x in probability. Then there exists a subsequence xn k, okay, k equal to 1 to infinity, such that xn k converges to same x almost surely. Okay, proof. So we have it converges in probability. So from that we want to conclude this. This just mean xn minus x greater than or equal to epsilon goes to 0 as n goes to infinity. Okay. This is just a number. Probability of this goes to 0 as n goes to infinity. That's what we have. So this you can replace by 1 by k. Okay. This goes to 0 for fixed k. Okay. For k in n, for any k in n, this is true. Epsilon you can replace by 1 by k. So this is true for each k. Okay. So each k you can make it less than anything you want after some time. That's what it means. Okay. So for each k, now you can write it, doesn't matter, but I'm just writing the main statement. For k in n, there exists a nk, okay, in n. Of course, nk you can choose to be increasing in k, such that probability of x and k minus x, I mean, it's after that this is satisfied, so you can choose to, I mean, greater than 1 by k is less than 1 by 2 power. Okay. This sequence goes to 0 for each k, so you can make this less than this for some nk and after that also. So for each nk it happens, then you can choose the this nk, small nk increasing. Okay. So that this is, so you have got a subsequence x and k. Okay. For each k you have an x and k which satisfies this. You have got a subsequence. You have to show that this subsequence converges almost surely, right? So from the condition that it converges in the probability, we have got a subsequence which satisfies this. Okay. Okay. Now we have to show this. So what we do is the following. So I mean, you can take 1 by k square if you want, whatever. We want to sum it. That's all. That's the basic. So this implies this is less than 1 by k. So summation n equal to 1 to infinity, probability of that x and k minus x greater than 1 by k, greater than or equal to 1 by k is less than infinity. Okay. Because it's Index is k equal to 1. Yeah. So this is less than infinity. So we know the Borel-Control lemma, which we have proved, which we have used also. This implies lim sup of this set, probability of this lim sup of this set, which is this set, x and k minus x greater than or equal to 1 by k is 0. Okay? Probability of lim sup of that set is 0. Lim sup is in k, of course. Okay. So, okay. So this set has called this as set of A, and probability of A equal to 0. And we want to show that in A complement it converges. That's all. That's what we have to show. Because almost sure convergence means that. So A complement is equal to what? A complement is complement. I mean, this is intersection union. So that will be union intersection. So this is just k equal to 1 to infinity intersection of k, say L equal to k to infinity. Okay, and this is x and k is a complement. Okay, less than 1 by k. Hmm? Yeah, lim sup. Yeah, a equal to this. A equal to this, probability of A is 0. Okay. Hmm? Then the complement of this just lim inf basically. Lim inf is this, k equal to 1 to infinity, this is this. Okay. Now if omega is in A complement, that means omega is in one of these things. Omega is in one of these things. That means it's in all of these things after some time. So, eh? Yeah, L equal to get. I mean, some index. Yeah. So then it should be L. Okay. Hmm. Okay, it should be L inside. Okay. So omega is in A complement means omega is in one of this K. That should be in all of this L. Okay. That is there exists for omega is in that, omega is in this set. Okay. In for all L greater than some Nk. So for omega instance, let me write it. There exists a Nk such that for all L greater than or equal to Nk, this XNL minus X is less than 1 by K. 1 by L. Okay. Yeah. Okay. Okay. For all L greater than this. Huh? That's not what I want. Wait. No. There is some mistake. What is that? Yeah, that's okay. That's okay. So that's XNL minus X goes to 0. This also implies, no? Is there a mistake? This is the lim sup of this. Lim inf of this is k equal to 1 to infinity, L equal to k. This is okay. Here, for omega is in A complement, omega is in somewhere here. So there exists a Nk. This happens, I mean, this is Nk. L starts with Nk. It's in all of these things. So it starts with Nk. There exists a Nk such that it is in all of them. No, this is less than, sorry. This should be K only, no? Wait a minute. For all omega? For all omega. If, yeah, for any fixed omega. For each omega, it will be in one of these things. This n omega, I mean, some arbitrary omega here, that should be somewhere here. For each omega, this NL will vary. That will depend on that. Okay. So this is a XNL minus X is less than 1 by L. Okay. XNL will converge to X as n goes to infinity, right? This is okay. Omega. Okay, maybe you put a omega here. This is for omega. Okay. Writing it as a problem, there is omega. Where is denominator? It's a, this will go to 0, no? Oh, that's what I had. So this goes to 0 as L goes to infinity. Okay. Is okay. Is anything funny? No. Okay. Okay. That's all. So next we want to use something which I stated here. So this is proof is easy, but we want to deal with distributions, convergence distribution. So Xn converges to C. C is a constant random variable. A random variable taking constant in distribution. Okay. C is a constant random variable. So Xn is a sequence of random variable converges in distribution to a constant random variable. Then the convergence to C in probability. Okay. Proof very simple. So we have to prove that fxn converges to what is constant random variable C. It converges to fc of x equal to 0 if x is less than C. fc of x equal to 1 if x greater than or equal to C, right? Probability of x strictly less than C is 0. X equal to C is 1, so it's after that it's 1. Okay, this is the fc. Huh? Yeah, for constant random variable, not always, but this constant random. So convergence in distribution means this. Okay, for all continuous random variable, for x that is the only x not equal to C, this happens. Okay. Okay. Now probability of xn minus C greater than xn minus C greater than or equal to epsilon. Okay, greater than epsilon doesn't matter. Okay, is equal to probability of xn minus C less than minus epsilon. Okay, plus probability of xn minus C greater than epsilon. Okay. X not equal to, that's a continuous point. It convergence happens only at continuous point. Okay. You can, okay. The convergence in distribution is defined that the distribution function converges at all continuous points of this. The continuous points of this is x not equal to C. Okay, that's what it, right? That's how the definition of convergence is. Now this is less than C, this is. Now xn minus C less than epsilon. Okay, I mean it's clear. Xn minus C less than, it's clear. This goes to 0 at x. This is right. This is equal to f. I mean, this is just probability of xn minus C less than epsilon, which is xn less than or equal to C minus epsilon. Okay. Probability of xn greater than C plus epsilon. Okay. This goes to, I mean, this goes to what? This goes to 0, right? Strictly less than C. fxx goes to 1 if x is strictly greater than C. Okay. Right? That's what this means. Okay. Fxn converges, it goes to 0, x less than C. At C, there is no convergence. There need not be any convergence. So, exactly this. So, C minus epsilon is C minus epsilon is strictly less than C. Okay, epsilon greater than 0. So, this will go to 0. This is strictly greater than this, but it is 1 minus f of that, right? This is equal to 1 minus p of xn less than or equal to C plus epsilon. Right? This is 1. This goes to 1. 1 minus 1 is 0. So this also goes to 0. Okay. That is what he said. F of X goes to 1 if X is greater than C, strictly greater than C. F of, no, this is the F of Xn at C plus epsilon, which goes to 1, like that. This is F of, right? This is equal to Fxn at C minus epsilon. This is equal to 1 minus Fxn at C plus epsilon. Okay. This goes to 1, that goes to 0 because of. Okay. So we want to use log of complex number in a small thing. So I want to review that, which either you must have seen or you will see later, okay, in the complex analysis course. So if Z is in this set, mod Z is all Z such that, I mean, yeah, guys, let's call it D11. This one is one considered as a complex number. This one is number 1 in real number. Both are same. What I mean is the following: all those Z such that mod of Z minus 1 is less than 1. Okay. We have 1 here, it is just this. Okay. Mod of Z minus 1 is less than 1. D11. Disk with center 1, radius 1. Okay. Disk with center 1, radius 1. D11. Yeah, you can do that. For our purpose, we use this domain. Okay. Then you define log of Z in this for a complex number, Z in D11. For other things, we may need to define slightly different. Okay. Otherwise, I mean, you can see that imaginary part, negative part of the imaginary part also, this makes sense for all these things. Log of Z equal to Z minus 1. I mean, this is the basic Taylor series around 1, which you replace X by Z. That's all. You define it like that. Okay. Z minus 1. And then Z minus 1 by 2 plus Z minus Z minus 1 square by 2, Z minus 1 cube by 3, minus, there is no 3 factorial because when you do that, that will all cancel. You know that. Okay. Z minus 4 by 4 goes on like this, alternate plus or minus. This is clearly convergent because that itself Z minus 1 is less than 1. Mod of Z minus 1 is less than 1. So clearly it's convergent. I mean, it's absolutely convergent. So this is also convergent. So that is clear. Then this is the usual complex e power Z, which you know is equal to Z. Okay, let me not go through this. Okay, you agree with that. And if you have a phi, it's a function defined from 0 to, I mean, minus t to t, okay, some function such that it takes the value inside this, okay, some function, okay, then log of phi t makes sense, okay, because it takes values inside this. Log of phi t, you can make sense. So then d by dt is 1 by phi of t. Remember that t phi is a function of t, not a complex value, a function of it. So the differentiation happens with respect to the real real variable only. Okay. So I mean, complex variable also these things is true, but still we do it only real variable. So these things are not anything complicated. So this is equal to phi prime. Then you differentiate that. What domain? D11. This is this. It takes minus some interval defined on minus tt around 0 and then takes values here. Minus t to t. Just an open interval minus t to t. It is just defined on that. Any interval is fine, okay, because we will deal with minus t to t. So that's why there is nothing about minus t to t. D is here. What is t? T is a variable. Phi of t. T is in this. Sorry, maybe minus. Okay. Sorry, this is okay. t is the independent variable with respect to which we are differentiating, and this is true. Okay. Okay. Now our characteristic function t is real. It takes values. It's a complex valued function. That's what we are dealing with our characteristic function. We want to, the only place where we use complex numbers are characteristic function. So that's the only place. Okay. So that is what, that's why we need. Okay. Now phi is a complex number which is from R to C, right? R to C. And phi is continuous. I mean, this is a characteristic function. Okay. Let me write, sorry. X is a random variable. Okay. Then phi x is a function from here to here, complex valued function. And phi is continuous. We have proved this thing. Phi is continuous. And phi of 0 is 1. Okay. So phi is continuous and phi of 0 is 1. So there exists a or epsilon or delta, whatever. Okay. Doesn't matter. You can take delta. A, but the epsilon is big. It's 1. So a, not this is this one, the other one. This one is the complex number 1, the other one, radius 1, we are going to use. Okay, that is the epsilon. Okay, I mean, which one? There are all ones are same, but we are using the radius 1 as epsilon. I'm using the continuity. Okay, there exists a in R such that phi of this minus a, this interval, okay, sits inside d of 1, 1. Okay, this is a disk with radius z, I mean with radius, I mean center 1 and radius 1. Okay, take epsilon equal to 1. This is a complex valued function. If you want, you treat both imaginary part and real part different, and they are continuous. I mean, if phi is continuous, if only real part and imaginary part both are continuous, and from that here in this case you can do that, and phi x characteristic function, characteristic function. That's what we have been using consistently. We are using. Yeah, from R to complex number. Phi is continuous, and phi these properties we have proved. Or for any function which satisfies this, this is true. Okay. Phi is a characteristic function. Phi is continuous. We have. Yeah, it's good. You have questions and you convince yourself. Good. Okay. Now, because of continuity, epsilon is 1. There exists a delta such that this happens. Okay. This is just I'm using continuity. Given epsilon greater than 0, there exists when x minus that a is less than some delta f of x minus something f of a is less than epsilon. Epsilon equal to that 1 and delta will be this. Okay. So by continuity, we get that. So we can near 0. So log of px is well defined in some interval near 0. Okay? In some neighborhood, that means an interval, neighborhood, an interval where the 0 sits inside, not in the corner points. That's okay. Neighborhood around 0. Okay. That's all. That's what I mean. There is no assumption. It's all fact. What is the assumption? What is the question? X is a random variable, Px is a characteristic function. It satisfies these two conditions. So there exists a around a which is positive. A is positive. Okay, a is positive such that phi of minus a is contained in that by continuity. So on this interval, log x is on, I mean, on the neighborhood which is minus a if you want. Okay, on this the log is well defined, and that's all I'm saying. What are you confused still? That's all. That's all. Okay. So that's what we want to use. Okay. So log of the characteristic function, because when whatever the characteristic function mostly we have, it is e power something, right? Because we are integrating e power something and everything, we get e power something. So it's better to take the log and work with whatever sitting on the above exponential. Okay, sitting inside the exponential. Okay, so that's why we do this. That is precisely the log, and that we can take limits and easy. So this is something we must have seen earlier, but I am proving it. If E x is a random variable, of course, and E mod xn is less than infinity, okay, then depending upon n is even or odd, oh, that doesn't matter. We will use the then d p t divided by dt. You take the nth derivative at t equal to 0 equal to I think this is right. We will verify this. There is no mod here. Okay. Yeah, minus I. Minus I. Yeah, there is no minus. I power n ex. Proof. I hope you remember this. I will write here. If you want to have a function which is of two variable, okay, two variable function. Suppose this is a two variable, okay. Suppose f of xt mod of this is less than or equal to some g of t, g of x, sorry, for all t, wherever the t ranges. And also this function dou f xt by dou t, okay, mod of this is less than or equal to h of x for all t. Yeah, then I mean this also, this is a function of t, so it's for all t. Okay, then d by dt of integral f xt dt. I'm writing this because partial differentiation, because there are two variables. Okay, otherwise it's the same thing. Okay, is equal to integral dou f by dou t f xt dx. We can take the derivatives inside. Same dominated convergence theorem. Huh? No, this is a general fact. Huh? Let's see. I power n. X power n, yeah. E of x power n. E of x, not E of x whole power n. E of x power n. Okay. F of? No. There is no by anywhere. Okay. I'm just saying you take the derivative, you take the function is bounded. I mean, without this t, it should be uniformly bounded by one single function. And of course, f and g are integrable. Integral f is less than infinity, integral g is less than infinity, integral h is less than infinity. Okay. I mean, wherever that limits are, okay, mod f. I mean, it should be mod because it's already positive. It's bounded by that, so it should be positive function. Yeah. Okay. That's all. So uniformly in T, uniformly in this. This is the dominated convergence theorem. This follows from the original dominated convergence theorem. You can, I mean, this is just a limit, but one of them is not enough. You need this condition. So if you do it n times by induction, okay, this is then, okay, we can do it n times, the same thing, provided n times that is bounded by that, okay, for all of them or something, okay. So we will use that. So what do you have? P of t equal to integral for continuous variable. I mean, this is true for discrete one also, okay. This is just e of, let's see, e power, but either it will be a sum or integral. Both it's true, okay. Instead of this integral, if you have a sum over x, then also the same thing will do, except that this will also be sum, this will also be sum. Sum or integral doesn't matter, okay. So let's use integral so that the same thing will hold for sum also. This is just e power itx f of x dx, okay, where f is the density, okay, f is the density, okay. Now you can see that this is a two variable function. Okay, e power I t x f of x mod is equal to f of x. Okay, and this is integrable. Okay, because it is a density function. Also, if you differentiate this it once, if you differentiate it, you get ix. Okay, right? Or dou n of this e power I t x f of x by dou t n, you will get ix power n. Okay, times e power I t x f of x. Okay, if you differentiate it n times or one time, you can see once n times, you get e power ix n times. Okay, so ix power n e power I t x this. If you take the modulus of this, ix, this will go away. This is just mod x power n, just f of x. This is also integrable if this condition is satisfied. Okay, so you can take the derivative inside. That's all. You can take the derivative inside. So if you want you to look at it for n equal to 1, it's clear. Okay, n equal to 1 is clear. If you differentiate once, you will get only get ix. If you differentiate this, there is no t anywhere else, only here. So you get ix. And if you take the mod, I will go away, e power it will go away. There is no t anymore. It's only f of x, x power x in f of x, and that is integrable. Okay. Okay. So we'll go there. Incidentally, this uses something called mean value theorem. Okay. This is not for this does not directly follow. You have to use mean value theorem to get to this. This is the fact. This is the theorem. This is you. This, I mean, if you just want to take a limit, one condition is enough. If you want to take the differential inside, you have to use something. Something you have to take something quotient. I mean, divided by t. You have to take the limit something inside. But that is equal to f prime of something is a mean value theorem, and because of mean value theorem, you can take the limit inside. Okay, you if you work it out, it will be clear. But you will see this later anyway in your life if you are going to do mathematics. You can't avoid this. In any field of mathematics, if you work, you have to see this. Of course, physicists don't need. You can just take limit, just like that. Okay. So what do you want? So this now it's clear. Now that is the statement. Okay. Tn p of t by dt n equal to ix power n, right? Integral ix power n, whatever, minus infinity to infinity, whatever. I haven't written the limits. You can write it. Okay. Minus infinity to infinity, ix power n, then e power itx of x dx. That is equal to I power n. So this is just e x power n. This is the definition of ex power n. Right? At t equal to 0. I mean, at t equal to 0. This is equal to, okay, let's write it. I integral, I mean, if you take t equal to 0, fx dx, right? That's what I would have done like that. So at t equal to 0 equal to this. At t equal to 0, this will become 1. Okay. Okay. That's all. That's what I have written. Characteristic function. I mean, this is equal to, sorry, I haven't written it. So this is, yeah, this is the phi nth derivative at 0. Huh? Wait. No, what have I written? Yeah. No, no, no. So that's what this is. This is nth derivative at 0 is equal to I to the power n e x power n. From this equation. That's what I want to. Is okay? This is this, that is that. Okay. Okay, okay, we will use this. Okay. Okay. Now, as I have said, we have that log phi of t, whatever, for x is a random variable. This is again a proposal. Question? So next proposition, maybe a lemma. X is a random variable. Okay. Then phi x, we can make sense of log of phi x near 0. So let's not write all those things. Let's just take it like, write it like this. Okay. Log of phi x t, which is near 0, divided by t, limit t going to 0, equal to, I think it is I e of x. To be clear from that. Yeah. This is just, I mean, there is nothing in this. This is just limit, whatever I have written is just the derivative, right? Log of limit t going to 0, log of pxt by t. Pxt at 0 is 1. So log of 1 is 0. Yeah, that's what I'm saying. It is immediate. I'm just writing it in terms of the limit. That's what I'm saying. But you have to have phi prime xt something. I mean, so this is log of phi xt. I mean, we have to substitute p at 0 is 1 from that. It follows from that. That's what I'm saying. Okay. So this is just d log pxt by dt, right, at t equal to 0, which is just phi prime xt x0 at phi prime 0, okay, which is just I e of x. Okay. Right? Because of that. Okay. This is okay? Okay. Now we prove weak law of large number in general. Hmm? What? Yeah, maybe I'll do that. Is that what you said? I thought there will be more space. Once I have written it, we will remember that, and there will be more space here. Okay. Theorem. Weak law of large numbers. If you do the experiment large enough, it will approach the mean. That's all. Okay. X is a random variable with, let's call it mu, Ex equal to mu. There is, you have to write it. Ex is a number, mu. Then, not, sorry, I need independent one, no? Sorry. X1, X2, X3, a sequence of IID, independent and identically distributed. I've used this word several times. Distributed random variables with EXI equal to mu. Of course, they all have the same mu. They have the same distribution, so they have the same expectation, which is mu. Then, and Sn equal to, I mean x1 plus 2xn. Okay. Then Sn by n. Okay. This is how we compute probabilities, minus mu, or xn minus n converges to mu is also fine, goes to 0 in probability. Both are same. I mean, Sn by n converges to mu, okay, or You can write it like this. That's better. Sn by n converges to mu in probability. Okay. You have a sequence of independent and identically distributed random variables, IID random variables, each with mean, only the mean assumption, mean exists, and EXI equal to, I mean, with first moment exists. When I say EXI equal to mu, it exists also. Okay. So it exists. Then you take the sum divided by n, that will converge in probability to mu. Okay. So this is the statement. Proof. Since this is constant random variables, is enough to prove Sn by n minus mu converges to 0 in distribution. Okay, because we have proved that convergence in probability same as convergence in distribution for constant random variables. Okay, when the limit is a constant variable, not for all, when the limit is a constant random. Okay. Okay. So we just have to prove this distribution of this. We have to compute the distribution of this that converges to 0. But we have proved a continuity theorem in for characteristic function. So it's enough to prove to take the characteristic function of Sn by n minus mu at t that goes to 0 for all t. So for goes to 0, yeah, 0 for all t. Goes to 0, right? That should go to 1. Okay. Yeah. For all, this is a characteristic function. For all, phi xn for all, for every t as n goes to infinity. This is the. Huh? The characteristic function equals a function equal to the 0 is by default that. Yeah. No. This for each t, this function will go to 0. Yeah, but that's what that is the statement. The statement is for each t, when you fix t for each t, okay, this goes to 0. Okay. So you have to compute the characteristic function of this and then do this. So what is phi Sn equal to phi of x1 power n, right? Okay. And phi Sn by n at t equal to phi of phi Sn at t by n, right? Because this is just e power ixt you will have, but then if this is by n, so it will be t by n, so this is okay. Phi Sn is just the sum of n random variables, so phi x1 power n. Okay. And this is you can multiply a random variable by some constant, that will characteristic function, it will come here, because if you multiply a random variable constant will come here. Okay. That constant you can club with t and you get that. Okay. So phi Sn by n, this is Sn is a random variable, Sn by n is a random variable. Phi Sn by n at t is phi st by n. Right? Yeah. They are all identically distributed, same distribution. They have the same distribution, they have the same characteristic function. Yeah, that's why they are all IID. Same distribution, same mean. If variance exists, that's also same. Everything is same for okay? Same distribution because of that. Okay? Now phi of S and T. Now this is equal to phi of x1 power t by n power n. Okay? Of course, phi of Sn by n minus mu at t is equal to, you have to multiply with e power minus I u2. This is equal to e power minus I mu t times phi of x1 at t by n power n. Okay. Now we want to prove this goes to 0. Okay. So enough to prove log of this at t is equal to this, which is just log of Px1 over, so n times this Px1 power t by n, okay, minus I mu t. Okay, this goes to 1. Okay, something goes to 0, log of that should go to 1 because it's all continuous operation. It's in fact 1 1 and other things. Okay, right. So for that I keep the n outside and I put another t by n here. Okay, this, yeah, something goes to, oh yeah, that is right. Sorry. I'm sorry. You are right. Yeah, that should be 1. So this should go to 0. Sorry. That is 1. The characteristic function of 0 function is 1. Sorry. What I said is not correct. This should, in distribution, this should go to 0. Characteristic function would go to 1. Good. Sorry. Yeah, I was, yeah, I missed it. Yeah. This distribution, it goes to 0. Okay. Anyway, I would have corrected it later because I will not get the right answer when you do that. So this should go to 0 in distribution, but this is a constant random variable 0, which is a e power 0 is 1. Okay, so integrate 1 with something, you will get 1. So this characteristic function of 0 random variable is 1. Characteristic function of constant random variable mu u is e power I mu t. So mu equal to 0, so it's 1. Okay, that's all correct. So this should go to 1. So this should go to 0, right? So this should go to 1. Okay, yeah, characteristic function should go converge to 1. Yeah, that's right. Okay. So we want this thing goes to 0. Oh, this thing goes to 0, right? Yeah, that's what. So we want to use what we have done here. Maybe we want to use this, right? We just want to use this. Okay? We want to prove this goes to 0. For this, we want to use this. This says the following: limit t going to 0. In this case, Ex is mu, which is just log of, I mean, you can, this is just a constant. There is no t inside. You can take it inside. Log of phi xt minus I mu. You can put a t here and divide it by t. Okay. I mean, you can put a t here divided by t. This limit going to 0 is 0. That's what this is. Okay. Now I can write the proof of that here itself. So this we have e power log phi xt for any random variable. Any random variable, log of phi xt minus I mu t by t is 0. The same statement I have written it like this. So this is mu. Okay. Now we just get it here. So we just want to prove this. Okay. Now notice that this t by n goes to 0. Here we have a t by n, here we have a t by n, but if we have a n here, so we have to bring it down with a t by n there. So what we have there is, I mean, this is continuation of this. Okay. I don't want to write it. Okay. This is equal to phi. Oh no, how much time? I forgot. Okay. I don't know how much time it went, but anyway, this is the weak law of, you can pause it and read it if you want. So it is just weak law of large number, which we have defined like this. And for that to prove, I mean, we want to prove that Sn by n converges in, we have a random independent IID random variables and the sum is Sn, and Sn by n converges in probability to mu. That's what we want to prove. So to prove that, it is enough to prove that because mu is a constant random variable, it is enough to prove that it converges in probability. And to, I mean, it converges in distribution. So for that, we need to prove that the characteristic function converges. So for that, we are using these things. Okay. Anyway, so unfortunately, I was trying to write here because thinking that it was pointing here. That's okay. So now we have to prove All we prove is we have to prove that this goes to 0. And that follows from this. We already have this pxt minus I mu t. Did I, when I was doing this also, the Pramana was not pointing out, I believe. Okay. Anyway, we can't help. So now this is just what we have. When I copy it, it is just, if I write it in a different way, log of p x1 times t by n, okay, minus I mu t by n by t by n times t limit n going to 0, infinity. Okay, n going to infinity. I put a t outside. I put a t here. So I have to do a t here, which I can take it out. Okay, it's only in n. The limit is in n. So this is okay. Now this goes to 0 because this goes to 0 as t going to 0. Right? Limit t going to 0. No, sorry. Which is here, sorry. This, as t going to 0, this going to 0. So because of that, this, and if n goes to infinity, this goes to 0. We have a t, doesn't matter, it will be 0, so it will be 0. Yeah. Okay. We approve. Okay. Yeah. We proved that fact, and then this fact. Yeah. And then we prove this. Okay. We are done. This is very easy. Easier than the earlier proof. Once we use characteristic function, this is easier than the earlier proof, right? Outside. This is all easy, no? No, not characteristic function. These properties, maybe. This property, this. Yeah, that's all. That's enough. No, not more. You don't have to define log and come through that. Yeah. Yeah. No. If it is 50 marks are given, then you have to prove it. If it is just 10 mark or something, then you have to prove it, depending upon how much is that. Okay. Now we want to prove central limit theorem. So we want to prove a similar limiting thing with second variable. Central limit theorem says that if you have a IID random variable, then you Sn by something. You make Sn, you have Sn. Sn is something, if you have an IID random variable, if each xi's, x1 up to xn, they are all IID, and each of them have mean mu, mean something, then you have to, this will have, you want to say something converges to normal 0, 1. Okay. So this has mean 0, variance 1. So you have to have something here to make sense. You have to have something here which has mean 0 and variance 1. So to make mean 0, you subtract n mu from this. And then variance you want to, so this has variance n times sigma square. So you want to get something less than that. So equal to that. So this should be the sigma is the variance you have to have. This random variable will converge in distribution to this. That is the central limit theorem. Okay, that's what we want to prove. Okay, I will write it again. Okay. To prove that, we need the following lemma. So we will compute it. I don't remember exactly what the lemma is. It is just we have to talk about the second. Now we will encounter something like this. X is any random variable with two moments exist. Okay, e of x square less than infinity. So you remember that if e of x square exists, e of mod x also exists. That you can prove. The same way we proved for discrete random variable, you can prove it. Okay? You remember the proof for discrete random variable? If e xn is less than infinity, then e xr may be mod. If it is odd, we need mod. Okay? If e xr is also less than infinity, for all r less than or equal to n. Exactly, same thing will work. We have proved the monotonicity of expectation. If x is less than y, ex is less than ey, and you can use the same thing. You take the, yeah, that's right. So, so because of that, if I assume ex square is less than infinity, E mod x also exists. Okay. Then log phi of x, then log phi x. So what do we have here? We have I mu, I mu. We will have I believe it is this, okay, by t square goes to, we should get the standard one, so it should be this. Yeah, these are all numbers, these are all functions, okay. The sigma is, this is equal to sigma square, okay. We have a random variable such that ex square equal to sigma square, and then you take the log of phi x minus I mu t divided by t square goes to this as t going to 0. Okay, okay, around huh? Mean is mu. Mean is mu. Mean 0 means you don't need this. So, huh? What? Why? Yeah, yeah, but that's another statement. This is one statement. Okay. But now will you consider with that? Then yeah, e power I something will come. Yeah, you can consider. Yeah. Okay. Okay. Now what do we want to do? We have right. Yeah. What is the problem? Huh? Oh, ex square equal to right. Good. That's why you are asking. Very good. Ex minus mu square equal to sigma square. Is that what you are worried about? Right? That's right. Good. Yeah. I will, anyway, I will end up in a problem later. So I will need this. Good. Yeah, this is right. Ex minus, so you are alert. It's good. Okay. So this will imply that this is of course ex square minus ex whole square. This just implies ex square equal to sigma square plus mu square, right? Okay. Right. This is good. Okay. Okay. Now we want to compute this. Okay. This is just, I mean, this is I remember from just normal random variable I have written. Do we get a t? Let's see what we get. But t going to 0, so it will not be. Okay. Let's compute what it is. Okay. We have this log phi x t minus I mu t divided by t square, limit going to 0. We use, how do you call it? When I was young, I used to call it L hospital rule, but you know that it's not. You may be knowing better because I am from a village kind of place. I read it through book, so I don't know his name. It's a French name. I don't know. So, well, how do you call it? Huh? Oh, very good. Okay, that is what I'm used to. Hospital rule. Okay, so you use that limit t going to 0. Later, when I know how to pronounce, even I learned some French. Still, I don't remember. I mean, I don't remember to call it the right way. Okay? Because I was used to that. So if you take the derivative, it is just px prime at t. Don't worry where it goes. I mean, divided by, I mean, because it's in the near the interval 0 where it is 1. So these things you can divide it like that. It will be positive px at t, okay, minus I mu, okay, divided by 2. Same thing. So limit t going to 0. This is just phi x prime t minus I mu phi x t divided by 2 p p. Okay. So this is also in 0 by 0 form. No, this is in what? Yeah, 0 by t equal to 0, it's 0. Yeah, 0 by 0 form. Okay, this is a okay because phi prime at 0 is I mu. Because of that, this is 0. Phi x prime at 0 is I mu. Okay, so this is also in 0 and p x t is 0. At 0 is 1. Eh? This is again in 0 by 0 form. That is also in this is also in 0 by 0 form. Okay, so the same reason. Okay. Now this is equal to, you have to differentiate again, limit t going to 0. If you differentiate it phi x prime t, okay, minus I mu phi x prime t, okay, there will be 2 of phi x prime t, 2, there is no this, plus 2t phi x prime t. Okay, I've just differentiated again, and you know that this at 0 is minus sigma square, I square is minus 1, minus sigma square, no, minus sigma square plus mu square, sorry, ex square is this is minus of ex square, this is minus of ex square, I square ex square, so minus of ex square, so this is my sigma square plus mu square, this is I mu, then there is a this is another I mu, so this will become plus, minus 1, it will become plus. So this whole, then there is, this is phi x t, this is 1 and this is 0 because t equal to 0. So I get the answer. So what do I get? I get at limit going to 0, this is just minus sigma square plus mu square plus mu square divided by 2, 2. So this is just minus sigma square by 2 as I want. Correct. You got it. Okay. Now the theorem. Okay. Random variables with e x1 equal to xi equal to mu p xi variance of right equal to sigma square. Okay, then Sn minus n times mu divided by n sigma times root n goes in distribution to, I mean, a random variable. If you want, you can use it, where z follows normal 0, 1. Okay. It goes to some random variable z such that z follows this normal 0, 1. Okay, we have to prove characteristic function converges correspondingly. That's what you want to prove. Want to prove characteristic function converges. So phi of, we have to compute phi of Sn minus n mu divided by that. So let's do one by one. Phi of Sn, okay, let's write it, sigma root n minus n mu by sigma root n, whatever, doesn't matter. So that is equal to at t. This is constant. So e power minus I mu t by, I mean, there is a square root n. Because we will get a n here. This will be power n. So let me keep it here. T by sigma root n. Keep it like this. Okay. Then this is going to be phi x1 power t by sigma root n power n. That's all, no? Phi Sn is phi x1 power n. Okay, phi Sn by sigma root n is phi x1 power n evaluated at t sigma root n. Okay, that's what. And this is counted here. It's just a constant. You have to put a I before that, IT before that. That's all. I, N, mu, everything is here. Okay. So this consists, this is constant, which is here. This is Sn is x1 up to xn. This is power n. They all have, they are IID. So this is okay. Okay. Now log of this. I am again take log of this. T, whatever there. This is equal to, I have a n outside. Okay. Then I have, what do you have? Phi x1 at T by sigma root n. Okay. Minus this I, n I have taken it out. So I mu T by the same sigma root n. Okay. Anything is missing? N has gone out. Phi x1 is phi x1 here. And then T by sigma root n is here. N has gone out because I have taken log. And I mu T sigma root n, there was a n here. That n has gone here. Okay. I have just taken log. Okay. Okay. Now limit n going to infinity. Limit n going to infinity. Okay. This is equal to just write it in the right form. Limit n going to infinity, right? Equal to, yeah, nothing. Okay. This is just P x1 T by sigma root n minus I mu T by sigma root n. The same thing I want to get it in the bottom. So which is just T by sigma root n square. Okay. So that I have to get here sigma. I have n there, which I have gone as root n square. I have a n here. That n has gone, I mean, in the bottom, the denominator is square root square. This is just T square by sigma square. Is there a minus somewhere? No, there is no minus. Minus, we will get it there. Yeah. This is okay. That's all. T square by sigma square. That's all. And we know that by whatever we have written here. Where is it here? This goes to 0 as T going to 0. Here n going to infinity. So n going to infinity means T by, T is fixed here. T, there is no, T is not going anywhere. It is just T by sigma root n goes to 0 as n goes to infinity. So this goes to, where is a log? Yeah. Of course. Of course, log is there. There is a log here, right? Yeah, sorry. Pardon. Okay. Yeah, there is a log. Yeah, I missed it. So now, because this theorem is for log, right? Log of this. Log of this. Yeah. So we have this log of this I mu something, some s or something, which is this here, which will as T going to infinity, that will go to where is it? T square. And that was a bracket. Okay. Okay. So this goes to minus sigma square by 2. That's what our theorem says. Minus sigma square by 2. Okay. So that whole thing will go to whatever we have. I will just write it here. Okay. This whole thing will go to minus, this is T square by sigma square is there. So T square by sigma square into minus sigma square by 2 will go equal to minus sigma square by 2, which is precisely, say it again. No, T is, there is no minus T square. Sigma square is minus sigma square by 2. There is T square by sigma square. This will go to minus sigma square by 2. Yeah, that's what. Oh, sigma square is correct. Sorry. Minus T square by 2. This is what you are saying. Good. Sorry. Yeah, this is normal 0, 1 is exactly that. Correct. Okay. And e power this is exactly normal 0, 1. Okay. Should I write? It's clear now. Okay, that's all. I thought I can do some conditional expectation, but there is less time, so I will stop. Okay. So this is the proof of central limit theorem. We have proved law of large number. We have to do some conditional expectation. Then whatever the remaining time, we will do Markov chain. Should we do? Okay. Up to you. We have already done